Welcome to this study of linear transformation lesson. In this lesson, we'll have a fundamental theorem in linear transformation that we are supposed to know and know how to use it. Okay, so first off, I want us to go through the proof of the theorem. So the theorem states that the name of the theorem is Dimension Theorem or Rank-Nullity Theorem. It states that let V and W be vector spaces and let V or T such that V maps to W be linear. If V is finite dimensional, then the nullity of T plus the rank of T is equal to dimension of V. How do we prove it? The nullity of T is the same as the dimension of the null space, and then the rank of T is the dimension of the range space of T, or the range of T. So suppose that the dimension of V is equal to n. Because V is finite dimensional, we know the dimension, right? And the dimension of the null space, because we can find the null space of V, which is the same as the nullity of T is equal to some k. And if you know the dimension of, or if you know the null space of linear transformation, then we can obviously find a basis, right? So we say that alpha equals this is a basis for the null space of T. We know by definition that the null space of T is also a subset of V. Then one thing we can do is that we can extend this. This is something I did not talk about, but in vector spaces, if you have something that is a subset, or some vector space that is a subset of a parent vector space, like null space of T is a subset of V, then we can extend the basis for that null space to form the basis for the bigger parent V, right? So we can extend alpha to a basis beta from V1 all the way to Vn to form another basis which will span, or which will produce or generate all of V. So then beta becomes the basis for V. So what can we say? We can say that one is show. So here we know that the dimension of V is equal to n. That is the number of vectors in beta, and that is n. The dimension of the null space of T, which is the nullity of T, is equal to k, right? The claim here is that we want to find the dimension of the range of T, or the rank of T, such that when you sum that dimension and then this k, you get n. Okay, the claim is that S, which is equal to the set of T of V sub k plus 1, T of V sub k plus 2, and then all the way to T of V sub n, is a basis for R of T. In other words, how many vectors do I have here? Right, all I know is that I have that the dimension of R of T, which is the rank of T, is now equal to, how many vectors do I have there? I have to just subtract n and k, right? And that'll give me the number of vectors. And indeed, if I sum this, that I'll get n. Notice that k, which is the nullity of, so here let me clean this and write it well. Nullity of T plus the rank of T is equal to, nullity is k plus the rank of T n minus k is equal to n, which is the dimension of V. Right? So with this claim, we are okay, but we don't know yet, because we know for sure that alpha is a basis for null space of T. Beta is a basis of V. Now the next thing we have to show is that we need to show that S is indeed a basis for a range of T, right? We cannot just claim it and go. So what do we need to show that something is a basis? First, show S generates R of T. Right? So how do we show it? from our previous video, we know that for a linear transformation and the basis for v, the range of t is equal to the span of t of beta, right? So we know what do I mean by this? We know that beta is the set of vectors that forms the basis for v, and given the basis of v, the range of t is equal to the span of all those vectors. So that's going to be the span of t of v1, t of v2, all the way to t of v sub k plus 1, and you go ahead t of v sub k plus 2 all the way to t of vn, right? The span of this. But we know that from v1 all the way to let me take that point again. Okay, I missed some things here. It's because I don't have enough space. All right, I'm gonna write it here. So this is equal to the span of t of v1, t of v2, all the way to t of v sub k, right? I wanted this to show t of v sub k plus 1, t of v sub k plus 2, to t of v sub n, right? The span of this, right? And this, we know that t of v1 is 0, t of v2 is 0, t of v sub k. So from v1 all the way to vk, all of them will be 0. So t of that and that, we're going to get 0. But if you have a spanning set that has 0 in it, we can throw it away because 0 can be part of the span, so we don't have to keep it. All right, so this, we throw all the parts that gives us 0 away, because this will give us 0, 0, 0 all the way to v sub k zeros. Okay, so this reduces to v sub k plus 1, t of v sub k plus 2, all the way to t of v sub n. So what have we shown? We've shown that indeed the range of t is equal to the span of that. It means that for every value you pick, so for, if remember, the range of t is equal to the span of that, it means for every vector, say u belonging to the range of t, right, what can you say? U also belong to the span of S, because if you look at the vectors we have here, there's a vector in S, right? What was S? S was defined to be this one, right? This is S here, right? So it means that every vector you pick in the range of t, that vector is being generated by S. I mean, that the meaning of the span of S means that every vector in R of t can be written as a linear combination of vectors in S, right? So that is the case. So it means that indeed S generates R of t, right? So that part is shown. Now, what do I need again to show that something is a basis? We have to second, we have to show that S is linearly independent, and then we'll be done. If you're able to show that, it means this claim is true, and indeed this works. Indeed, the summation of the dimension of the rank, or the dimension of the range of t, and then the dimension of the null space of t is indeed dimension of v. Okay, so to show this, let's start by using some claim. Okay, now suppose that, how do you show that something is a linear combination? We're going to suppose that we have a linear combination of vectors in S. Okay, suppose that the summation as I start from k plus 1 to n b sub I t v sub I equals 0. What it means is, I mean, if I is equal to k plus 1, you're going to have b k plus 1 times t of v sub k plus 1 plus when I, so I mean, you understand this, right? So yeah, I'm sure you get this. On the other hand, this is the same thing as, this is the same thing as b sub k plus 1 if you want to see explicitly what is happening, plus b sub k plus 2 t of v sub k plus 2 plus all the way to b sub n t of v sub n. That is what I've written it compactly here, or in compact form, that a summation of them should give me the 0 vector. So I'm saying that for me to be sure that this is linearly independent, it means all these b sub k plus 1, b sub k plus 2, all the way to b sub n, all of them should be zeros, right? I'm sorry. So suppose this is the case, right? Now I'm going to use this one because I just wanted to, I prefer that one. It's very compact and you can use it straight away. From that point, maybe let me call this one. From 1, what can we say? This is a linear function or linear transformation. So I mean, you can use a second expansion to see what I'm about to write. This can be, the one can be written as t of the summation as I start from k plus 1 to n, then b sub I v sub I. What I'm trying to say here is t is linear. Because of that, we can just shift the values in front of the t inside it, and it's going to be t of b sub k plus 1 v of v sub k plus 1, and then we push all the constants inside. Remember, we are using the idea that t of a v is the same as a t of v if t is linear, right? So if I have this, I can come back to this one, or if I have this one, I can go back to that one. So it works, right? That's what I'm trying to do here. So what happens again? Now this means that we have the transformation of some set of vectors, or a vector that is giving us 0. What does it mean? It means that, so this implies that this vector here is in the null space of T, because the null space of T means that every vector in the null space of T means that each transformation should give you 0. So if I have a vector that the transformation of that is giving me 0, then it means that vector is in the null space. So, but we know the basis for the null space, right? We've learned all these things. Then it means that the vector we are interested in, n b sub I v sub I, should be equal to the linear combination of vectors in the null, the basis of the null space, right? I starting from 1 to k, then ci v sub I, right? Now just check the index of I here, right? They are different, okay? So it means I'm going to have the summation I starting from 1 to k ci vi. If I take this sum, the sum on the left to the right, I'm going to have minus the summation I starting from k plus 1 to n b sub I v sub I is equal to 0. What does this mean? I can I can as well push in the negative, and I'm going to have some I starting from 1 to k ci vi plus the summation as I starting from 1 to k plus 1 to n negative bi, right, v sub I equals 0. And then this negative bi, we can call it, because negative bi is going to be a value, right? It's going to be a number. You can call it di. What does this then tells you? Or maybe we can still, let me replace it at negative bi, okay? Because I want to see the b sub I, negative bi v sub I, right? We have that. Now if you remember, so if you look at this from v1 all the way to vk, remember this, right? Beta is equal to v1 all the way to vn, right? And if beta is a basis for v, then it means every linear combination, if I have a linear combination of, so this, let me write it in words. What I'm trying to say here is, maybe you hear what I'm trying to say or you get it. What I'm trying to say here is that we have a linear combination of vectors in beta giving us 0, and beta is a basis. It means it's linearly independent, and this should mean that ci, all the ci should be equal to negative beta I, and all of these should give you zeros, right? And if you have negative beta I equals 0, it means that all the beta I should be equal to 0 in order for this to work, right? But we started from here, and we are saying that all the beta I should be 0, and if all the betas here, beta sub k plus 1 is 0, this is 0, that is 0, and we know that t of these guys are not 0 for sure, then what does this tell us? It tells us that it implies that S is linearly independent, because when we pick linear combination of all the vectors in S giving us 0, the only possible way was when all the coefficients in the vectors are equal to 0. So it means that S is indeed a basis for R of t, and the rank of this t, which is the dimension of R of t, gave us n minus k. That's what we got, right? And if you look at it very carefully, the nullity, I'm writing it again, we've done it, of t plus the rank of t is equal to n, because you're going to have k plus n minus k, and that is n, right? And so this proves the theorem that we stated, that if V is finite dimensional and T is linear, then this holds. So this is a very crucial result in linear algebra. I'm going to use it in more theorems to come up. Thank you for staying, and don't forget to subscribe to my channel if you have not. Okay, see you.